You exist in a universe that shouldn't make sense. Right now, as you watch this, you're standing on a planet hurtling through space at 500,000 miles per hour, inside a galaxy containing 200 billion stars, in a universe that stretches farther than light itself has had time to travel. And all of it, every atom in your body, every star in the sky, every dimension of space itself erupted from something impossibly smaller than the period at the end of this sentence. This is the story of the Big Bang, but it's not the story you think you know. You've probably heard it described as an explosion, a point in empty space that suddenly detonated, flinging matter outward into a pre-existing void. That's wrong. Profoundly, fundamentally wrong. The Big Bang wasn't an explosion in space. It was an explosion of space. It didn't happen somewhere. It happened everywhere. It didn't occur at some moment in time. It was the moment that created time itself. For most of human history, we didn't know the universe had a beginning at all. We thought it was eternal, unchanging, infinite in both directions of time. The idea that everything, space, time, matter, energy, the very laws of physics could emerge from nothing seemed absurd, impossible. The domain of religion, not science. And then we looked up, really looked, and the universe whispered its secret back to us. In 1929, an astronomer named Edwin Hubble made a discovery that shattered our understanding of reality. He was studying distant galaxies, measuring their light through the massive telescope at Mount Wilson Observatory, and he noticed something strange, something that shouldn't be possible if the universe was static and eternal. Every galaxy he observed was moving away from us, not just a few, not just the nearby ones. Every single galaxy in every direction was receding into the distance, and the farther away a galaxy was, the faster it was moving. It was as if the entire universe was expanding, stretching, carrying galaxies apart, like dots on an inflating balloon. You might think this means we're at the center of some cosmic explosion, that everything is fleeing from us specifically. But that's not what the evidence shows. Imagine you're an ant on that balloon as it inflates. From your perspective, every other ant appears to be moving away from you. But pick any other ant, and from their perspective, the exact same thing is true. There is no center to the expansion. Space itself is expanding everywhere simultaneously. This revelation changed everything. Because if the universe is expanding now, that means it was smaller yesterday. Smaller last year, smaller 1,000,000 years ago, smaller 1,000,000,000 years ago. You can trace this expansion backward through time like a film running in reverse, galaxies rushing toward each other, space contracting, matter and energy becoming denser, hotter, more compressed. Follow that thread far enough, and you arrive at an inescapable conclusion. There was a moment when all the space in the universe, all of it, the entire infinite expanse, was compressed into an infinitesimally small point. A moment when the universe as we know it began. But Hubble's observations were just the beginning. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were trying to eliminate annoying static from their antenna. No matter what they did, no matter which direction they pointed their equipment, they detected a faint microwave hiss. It was coming from everywhere at once, from every direction in space. Uniform, persistent, unchanging. They had accidentally discovered the afterglow of creation itself. This cosmic microwave background radiation is light that has been traveling through space for over 13.8 billion years. It's the cooled remnant of the intense heat that filled the universe in its infancy. You are bathed in it right now. Ancient photons that began their journey when the universe was just 380,000 years old are passing through your body at this very moment, carrying information about the birth of everything. The universe wasn't just expanding, it was cooling. And that meant it had once been unimaginably hot. When you rewind the universe, you're not just watching galaxies move closer together. You're watching the entire architecture of reality disassemble itself layer by layer, each step revealing conditions more extreme than anything you can imagine. Start with today. The universe is vast, cold, mostly empty. Galaxies cluster together in a cosmic web, separated by voids spanning hundreds of millions of light years. Stars burn quietly, planets orbit, chemistry happens. Life, at least here on Earth, contemplates its own existence. Rewind a few billion years, galaxies are closer together. Star formation is more violent, more frequent. The universe is brighter, denser, more energetic. But the fundamental physics is the same. Atoms exist. Light travels. Gravity pulls. Keep going. Rewind to when the universe was just a billion years old. The first galaxies are forming from vast clouds of hydrogen and helium. There are no heavy elements yet, no carbon, no oxygen, no iron. Every atom heavier than helium that exists in your body right now is still locked inside the cores of stars that haven't exploded yet. Further back, at 380,000 years after the beginning, something crucial happens. The universe has cooled enough that electrons can finally bind to atomic nuclei. Before this moment, the universe was an opaque fog. Photons couldn't travel freely because they kept scattering off free electrons. But once atoms formed, the universe suddenly became transparent. Light could travel. This is the moment captured in the cosmic microwave background, the oldest light you can ever hope to see. Before this moment, you can't see anything directly, but you can calculate what must have been there. Rewind to 3 minutes after the beginning. The universe is hot enough that atomic nuclei are being forged in a cosmic fusion furnace. Protons and neutrons are slamming together, creating the first helium, the first lithium. This process, called Big Bang nucleosynthesis, determines the ratio of elements that will persist for billions of years. The fact that our universe is about 75% hydrogen and 25% helium isn't random. It's the signature of these first 3 minutes, 1 second after the beginning. The temperature is 10 billion degrees. Neutrons and protons are just starting to survive as distinct particles. Before this, the universe was too hot, even for them. They melted into a soup of quarks and gluons, the fundamental building blocks of matter. 1 microsecond after the beginning, quarks are condensing into protons and neutrons for the first time. The fundamental forces of nature, electromagnetism, and the weak nuclear force are still unified as a single force. Physics as we know it doesn't fully exist yet. And then you reach the wall, the Planck epoch, the first 10 to 43 seconds after time began. At this scale, our understanding of physics breaks down completely. Quantum mechanics and general relativity, the two pillars of modern physics, give contradictory answers. Space and time themselves become quantum, fluctuating, uncertain. You can't rewind any further with current science. This is the horizon of human knowledge. But even here, at the very edge of what we can understand, we know something profound. You are tracing this history backward toward a point of infinite density and infinite temperature. A singularity. A moment where the equations break, where the universe was compressed into something smaller than an atom, smaller than a nucleus, smaller than anything. This is as close as science can bring you to the actual moment of creation. So what actually happened at the beginning? What was the Big Bang? Here's what we know, and what we're still trying to understand. In the beginning, there was no space, no time, no matter, no energy, nothing that you would recognize as reality. And then, for reasons we still don't fully understand, a quantum fluctuation occurred. Not in space, there was no space yet. Not at a time, there was no time yet. But somehow, from nothing, space and time themselves exploded into existence. This wasn't an explosion in the sense you're imagining. There was no fireball expanding into a pre-existing void. Space itself was born, and it began expanding, everywhere at once. All points in space were rushing away from all other points. And in this newly born space, energy condensed into the first particles of matter. The first moment we can describe with any confidence is the Planck time, 10 to 43 seconds after the beginning. This is the smallest meaningful unit of time in physics. At this instant, the universe was unimaginably hot about YP Kelvin, and all the forces of nature were unified as a single force. Gravity, electromagnetism, the strong and weak nuclear forces, they were all one thing. As the universe expanded and cooled, these forces began to separate, like water freezing into ice crystals with distinct structures. Then, at around 10 to 36 seconds, something extraordinary happened. Something called cosmic inflation. In an incomprehensibly brief moment, less than a trillionth of a second, the universe expanded by a factor of at least 1026. That's a 1 followed by 26 zeros. In that instant, a region of space smaller than a proton inflated to the size of a grapefruit or larger. This wasn't just rapid expansion, this was exponential expansion, driven by a special kind of energy field that filled all of space. Why did inflation happen? We're not entirely sure. The leading theory involves a quantum field called the inflaton field, which was stuck in a high-energy state. When it finally rolled down to a lower energy state, it released enormous amounts of energy, driving this explosive expansion. Inflation solved several profound mysteries about the universe. Why it's so uniform in all directions, why it's so geometrically flat, but it also raises new questions about what triggered it and what existed before. When inflation ended, the energy that drove it converted into matter and radiation. The universe was flooded with particles, quarks, electrons, photons, neutrinos. This moment is sometimes called reheating, because the universe went from the cold expansion of inflation to being filled with intensely hot particles again. You are made of the matter created in this instant. Every atom in your body, every particle, traces its lineage back to the end of cosmic inflation, when energy transformed into the building blocks of everything. For the next fraction of a second, the universe was a roiling soup of quarks and gluons, too hot for protons and neutrons to exist. Particles and antiparticles were constantly being created and annihilated in a chaotic dance of energy. Then, as temperatures dropped, quarks condensed into protons and neutrons. A tiny asymmetry between matter and antimatter we still don't fully understand why meant that a small amount of matter survived while most of it annihilated. That tiny excess became everything, every star, every planet, every atom in existence. By the time the universe was 1 second old, the first atomic nuclei were forming. By 3 minutes, the cosmic fusion furnace had created the first helium and lithium. And then, for nearly 380,000 years, the universe was an opaque fog of plasma, too hot for atoms to form, light scattering endlessly through the haze. When atoms finally formed and the universe became transparent, it was like a curtain being drawn back. The cosmic microwave background you can still detect today is the light from that moment, stretched and cooled by billions of years of expansion, but still carrying the imprint of creation. For 380,000 years after the Big Bang, the universe was blind. Not dark, the opposite of dark. It was so bright, so dense with energy, that light couldn't travel anywhere. Every photon that tried to move was immediately scattered by free electrons, bouncing chaotically like a person trying to run through a packed crowd. The universe was a fog of light trapped in itself. You couldn't have seen anything, even if you'd been there. Not because there was nothing to see, but because photons, the particles that carry light to your eyes, couldn't complete a journey. They were prisoners of the plasma, scattering endlessly, unable to travel freely through space. But as the universe expanded, it cooled. Temperature and density are linked to the scale of space itself. As space stretched, the energy within it spread out, diluted. The universe was like a gas expanding from a compressed tank. Rapid expansion means rapid cooling. By the time the universe was 380,000 years old, the temperature had dropped to about 3,000 Kelvin. That might sound hot. It is hot, about half the temperature of the sun's surface, but it was cool enough for something crucial to happen. Electrons, which had been zipping around freely, finally slowed down enough to be captured by atomic nuclei. Hydrogen and helium atoms formed for the first time. This moment is called recombination. Though that's a misleading name, it wasn't a recombination since atoms had never existed before. But the name stuck. When electrons bound to nuclei, the universe fundamentally changed. Photons no longer had free electrons to scatter off of. Suddenly, for the first time in cosmic history, light could travel. It could journey across space unimpeded. The universe became transparent. Imagine being there at that moment. For hundreds of thousands of years, you've been surrounded by an impenetrable fog of light, unable to see farther than your hand. And then, in a cosmically brief transition, the fog clears. Space opens up. You can see. The light released at that moment has been traveling ever since. As the universe expanded, that light was stretched along with space itself. The wavelengths grew longer, shifting from visible light to infrared, then to microwaves. By the time it reaches you today, 13.8 billion years later, it's been stretched by a factor of about 1,100. What was once the warm glow of 3,000-degree plasma is now a cold microwave signal, just 2.7 degrees above absolute zero. This is the cosmic microwave background, and it's everywhere. You can detect it with a radio antenna. In fact, about 1% of the static you see on an old analog TV screen is this ancient light, the afterglow of creation itself. You are bathed in photons that were released when the universe was 380,000 years old. Photons that have been traveling through space for longer than Earth has existed, longer than our sun has existed, longer than most stars in the galaxy have existed. When scientists study the cosmic microwave background in detail, they find something remarkable. It's not perfectly uniform. There are tiny variations in temperature differences of about 1 part in 100,000. These fluctuations are the seeds of structure. Regions that were slightly denser than average had slightly stronger gravity. Over millions of years, they pulled in more matter. Those tiny ripples in the fabric of the early universe are what eventually became galaxies, galaxy clusters, the cosmic web of structure you see today. You live in a galaxy that formed because of a quantum fluctuation during inflation, amplified during the first moments of cosmic expansion, and frozen into the structure of space when the universe became transparent. Your existence is written in the cosmic microwave background, encoded in temperature variations so small they were impossible to detect until the 1990s. The Big Bang didn't just create matter and energy. It created the blueprint for everything that would ever exist. Those tiny quantum fluctuations during inflation, random variations in energy density, smaller than anything you can imagine, were stretched to cosmic scales during the exponential expansion. When inflation ended, these fluctuations became real physical variations in the density of matter. Some regions were slightly more dense than others. The difference was minute, barely 1 part in 100,000, but it was enough. Gravity amplified those differences. Dense regions had stronger gravity, which pulled in more matter, making them even denser. Less dense regions lost matter to their denser neighbors, becoming even emptier. Over millions of years, this process of gravitational collapse transformed microscopic quantum fluctuations into massive structures. The first stars formed about 100 million years after the Big Bang, igniting in the densest regions where hydrogen and helium had collected. These were not stars like our sun. They were massive, hundreds of times more massive, burning ferociously hot and dying quickly in violent supernova. When they exploded, they scattered the first heavy elements into space: carbon, oxygen, iron, all the elements that would later make rocky planets and living organisms possible. These first-generation stars clustered together, forming the first galaxies. Small, irregular, nothing like the grand spirals you see today. Over billions of years, these proto-galaxies merged, collided, grew. Gravity drew them together into larger structures, galaxy groups, then galaxy clusters, then superclusters. The cosmic web emerged, vast filaments of galaxies separated by enormous voids, like the three-dimensional structure of a sponge. Every structure you see in the universe today, from the small dwarf galaxies orbiting the Milky Way to the great galaxy superclusters, stretching across hundreds of millions of light-years, traces back to those initial quantum fluctuations. The architecture of the cosmos was determined in the first fraction of a second of existence. Think about what that means. The galaxy you live in, the local group of galaxies it belongs to, the Virgo supercluster, the Laniakea, Supercluster. All of this structure existed as a pattern of tiny density variations when the universe was a fraction of a second old. The position of our solar system in the Milky Way's spiral arm, the fact that we orbit a star in a relatively quiet region of the galaxy, the existence of Earth itself, all of it flows from the initial conditions set by the Big Bang. But there's something else encoded in those initial conditions, something that determines not just where matter is, but what the universe will become. The density of the universe, how much matter and energy it contains, determines its ultimate fate. If there's too much matter, gravity will eventually overcome expansion, and the universe will collapse back in on itself in a big crunch. If there's too little, the universe will expand forever, growing colder and emptier until the last stars burn out and everything goes dark. There's a critical density, perfectly balanced, where the universe expands forever but gradually slows down. When we measure the actual density of the universe, we find something shocking. It's almost exactly at this critical value. Not 50% of critical density, not twice critical density. It's within 1% of perfect flatness. This is one of the great mysteries the Big Bang left us with. Why is the universe so precisely balanced? Inflation provides an answer. During that exponential expansion, any curvature in space was stretched flat, like blowing up a balloon until its surface appears perfectly flat at human scales. The universe could have started with any curvature, but inflation flattened it to the critical density. You live in a universe that is geometrically flat, that will expand forever, whose large-scale structure was determined by quantum fluctuations during a moment of exponential expansion 13.8 billion years ago. The conditions that allow you to exist, stable galaxies, long-lived stars, the gradual accumulation of heavy elements, were all set in motion by the specific properties of the Big Bang. Before we go further, we need to destroy some myths, because the way most people imagine the Big Bang is wrong in fundamental ways, and those misconceptions prevent you from understanding what actually happened. Myth 1: the Big Bang was an explosion in space. No, the Big Bang was an explosion of space. There was no pre-existing void that the universe expanded into. Space itself came into existence and began expanding. Every point in space is expanding away from every other point. There is no center to this expansion. There is no edge. If you could somehow travel fast enough to reach the edge of the expanding universe, you wouldn't find a wall or a boundary. You just find more universe because you're traveling through space that's expanding. Myth 2: the Big Bang happened at a specific location. No, it happened everywhere simultaneously, because everywhere that exists now was compressed into an infinitesimal point then. When the Big Bang occurred, it occurred at every location in the current universe at once. The Big Bang didn't happen over there, billions of light years away. It happened right here, right where you're sitting. The point in space you occupy now was once part of that initial singularity. You are sitting at the center of your observable universe, and so is everyone else, because the Big Bang happened everywhere. Myth 3: there was empty space before the Big Bang that the universe expanded into. No. Before the Big Bang may not be a meaningful phrase. Time itself began with the Big Bang. Asking what happened before time began is like asking what's north of the North Pole. The question contains a logical contradiction. There may have been something before our universe, some quantum foam, some multiverse, some higher dimensional structure, but we have no way to access information about it, and it may not even be describable using the concepts of time and causality that we're familiar with. Myth 4. The Big Bang explains the origin of the universe. Not entirely. The Big Bang theory describes what happened from about y-43 seconds onward. It describes how the universe evolved from an extremely hot, dense state to its current form. But it doesn't tell you why there was a hot, dense state to begin with. It doesn't explain the ultimate origin, why there is something rather than nothing, what triggered the initial expansion, what the laws of physics are the way they are. The Big Bang is a description of cosmic evolution, not cosmic creation. It's a theory about how the universe developed, not why it exists. Myth 5. The Big Bang contradicts the conservation of energy. This is more subtle. In normal physics, energy is conserved. It can't be created or destroyed, only transformed. So how did all the energy in the universe come from nothing? The answer has to do with gravity. Gravitational potential energy is negative. As the universe expands and matter spreads out, the negative gravitational energy increases in magnitude. If you carefully account for all the positive energy, matter, radiation, motion, and all the negative energy, gravitational potential, they may sum to zero. The universe may be, in total, nothing, just a highly organized form of nothing, with positive and negative energies in perfect balance. This doesn't answer the deepest question of why anything exists, but it does show that the Big Bang doesn't necessarily violate the conservation of energy. Understanding what the Big Bang wasn't is just as important as understanding what it was. It wasn't an explosion. It wasn't an event in space. It may not even have had a before. It's a description of how space, time, matter, and energy emerged and evolved, not a complete explanation of ultimate origins. And that's okay. Science isn't about having all the answers. It's about having the right questions and the intellectual honesty to say, we don't know yet, when we reach the limits of what evidence can tell us. There's a wall at the edge of what we can know about the Big Bang, not because we lack imagination or technology, but because the universe itself prevents us from seeing beyond a certain point. The cosmic microwave background is that wall. It's the oldest light we can ever observe. Before recombination, the universe was opaque. Photons couldn't travel freely. That means no light from earlier than 380,000 years after the Big Bang can reach us. Everything before that moment is fundamentally invisible to telescopes. We can't look further back in time with light, but we can look with other messengers. Neutrinos barely interact with matter, so they could have escaped the early universe even before recombination. If we could build sensitive enough neutrino detectors, we might observe the cosmic neutrino background, which would show us the universe at about 1 second old. Gravitational waves pass through matter without scattering, so in principle, they could carry information from even earlier moments. We haven't detected primordial gravitational waves yet, but if we do, they might tell us about cosmic inflation itself. Still, there's a deeper barrier, the Planck epoch. At 10 to 43 seconds after the Big Bang, our physics breaks. General relativity tells us that space-time is smooth and continuous. Quantum mechanics tells us that at small enough scales, everything becomes uncertain, fluctuating, probabilistic. At the Planck scale 1.035 meters, 10 to 43 seconds, both theories try to describe reality, and they give incompatible answers. We need a theory of quantum gravity to describe this epoch. String theory, loop quantum gravity, and other approaches are attempts to build such a theory, but none of them are confirmed by experiment. We simply don't know what the laws of physics are at this scale. This means we can't say with certainty what happened at the very first moment. We can't describe the singularity itself. We can't say whether time truly began at a single point or whether there was some kind of quantum foam before, or whether before even makes sense. The honest answer is, we don't know, and there are other mysteries the Big Bang leaves unsolved. Dark matter. About 85% of the matter in the universe doesn't emit, absorb, or reflect light. We know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters bend light from behind them in ways that require far more mass than we can see. The Big Bang Theory tells us that this dark matter was created in the first moments, but we don't know what it is. Not baryonic matter, protons and neutrons. Not neutrinos. Something else entirely. Particles we've never detected. Dark energy. About 68% of the energy content of the universe is something even stranger. It's causing the expansion of the universe to accelerate. Galaxies aren't just moving apart, they're moving apart faster and faster over time. This was discovered in 1998, and it defies explanation. It might be a property of space itself, a quantum energy inherent to the vacuum. It might be a new kind of field permeating the universe. We call it dark energy, but that's just a name for our ignorance. Together, dark matter and dark energy make up 95% of the universe. Everything we can see and touch and measure directly, stars, planets, gas, is just 5% of what exists. The Big Bang created it all, but we don't understand most of it. The matter-antimatter asymmetry. For every particle of matter created in the Big Bang, an antiparticle should have been created too. When matter and antimatter meet, they annihilate, releasing pure energy. So why is there anything left? Why didn't all the matter and antimatter destroy each other, leaving a universe of pure radiation? There must have been a tiny imbalance, about one extra matter particle for every billion matter-antimatter pairs. That tiny excess survived, and everything you see is made from it. But we don't know why the asymmetry existed, the flatness problem. Why is the universe so close to the critical density? Cosmic inflation explains this by stretching space flat, but that just pushes the question back. Why did inflation happen? What is the inflattened field? Did inflation occur everywhere, creating a multiverse of bubble universes, each with different physics? Or was our universe special somehow? These aren't failures of the Big Bang Theory. They're the frontiers, the questions that drive research, that fuel telescopes and particle accelerators and theoretical physics. The Big Bang Theory is one of the most successful scientific theories ever developed. It makes precise predictions that have been confirmed again and again. But like all scientific theories, it's not complete. It's a framework that explains what we know and points toward what we don't, and that's the beauty of it. We know so much more than we did a century ago. We can trace the history of the universe back to a fraction of a second after it began. But there's still mystery left, still questions to answer, still a horizon beyond which we can't yet see. You are standing in the afterglow of creation. Right now, as you exist in this moment, you're embedded in space that was born 13.8 billion years ago. The atoms in your body were forged in stars that formed from quantum fluctuations during cosmic inflation. The light falling on your skin left the sun 8 minutes ago, but it's made of photons whose lineage traces back to the primordial plasma of the early universe. You're breathing oxygen created in stellar furnaces billions of years ago, drinking water made from hydrogen that has existed since the first 3 minutes. Everything about you, the chemical elements that make up your cells, the physical laws that allow chemistry to happen, the structure of the galaxy that sheltered the formation of our solar system exists because of the specific conditions set by the Big Bang. The Big Bang wasn't just something that happened in the distant past. It's happening now. The universe is still expanding. Space is still stretching. Every second, galaxies move farther apart. The echo of that initial moment still reverberates through reality in the form of the cosmic microwave background, bathing you in ancient light. You exist inside the Big Bang's ongoing consequences, and you're one of the ways the universe has organized itself to understand its own beginning. Think about that. The matter and energy created 13.8 billion years ago has arranged itself through billions of years of cosmic evolution into structures capable of looking back at their own origin. Stars formed, planets condensed, chemistry became biology, biology became consciousness, and consciousness developed science, mathematics, telescopes, satellites, tools to decode the whispers of creation written in the cosmic microwave background. You are the universe examining itself. Your curiosity about the Big Bang is the universe's curiosity about its own birth. We don't have all the answers. We can't see past the wall of the cosmic microwave background. We can't describe the Planck epoch with confidence. We don't know what dark matter is, what dark energy is, why there's matter instead of just radiation, whether inflation created a multiverse, or what if anything existed before time began. But we know so much more than we did. We know the universe had a beginning. We know it started in an extremely hot, dense state, and has been expanding and cooling ever since. We know the first elements were forged in cosmic nucleosynthesis. We know when the first atoms formed, when the first stars ignited, how galaxies assembled from quantum fluctuations. We can trace the history of everything back to the first fraction of a second. And the story isn't over. New telescopes are peering deeper into space and further back in time. The James Webb Space Telescope is observing the first galaxies forming in the ancient universe. Gravitational wave detectors might someday hear the sound of cosmic inflation. Particle accelerators are searching for dark matter candidates.